just make sure to stay over there.
Sure.
So laser pointer backwards, forwards.
Cool, thanks. Alrighty, thank you so much, folks. And again, as Aaron said, I hope you can find it in your dark hearts to, find it in your hearts to forgive my dark heart. Something like that. Regardless, we're going to talk about some really dark things tonight. So I wanted to talk today about the classic image that has instantly become famous of this black hole here, that we have, first seen a few months ago. So probably a lot of us have seen pictures that are sort of similar to this one. This is a picture of a simulation of a black hole that actually showed up in the movie Interstellar in 2014. A lot of us have seen pictures like this, either of this or of like a disk with some like jets shooting out of it. And the reason I like this particular one is because they actually did some serious computational calculations to create these images for that movie, which is not something you get out of Hollywood very often. And so this is all very nice and good, of course. It's nice to have computer simulations that show us what a black hole might look like. In this case, we see a disk of material that surrounds that black hole. And the gravity of that black hole is so strong that the disk material that's behind it, the black hole from us is actually being bent around and out towards us again anyway. And so this computer simulation is all nice and good. But of course, it would be really great if we could see what a black hole actually looks like in physical reality. So for a long time, it wasn't even clear that black holes even existed. So if you were to step outside at night and look up at the Milky Way galaxy, and then you were able to zoom in by a factor of, 10 million or something like that, you would eventually come to the heart of our galaxy. And at the heart of our galaxy lives a black hole that we call Sagittarius A star. It's not a very fun name. It's not Josephine or anything terribly interesting. But it is there, and it weighs about 4 million times the mass of our own sun. And like all black holes, it's so massive and so dense that not even light can escape it if it crosses the event horizon. So as we are able to peer through all the material that surrounds our Milky Way, all of the spiral arms, all of the dust, all of these other stars, we eventually find our way to this star cluster at the very center of our galaxy. And inside this star cluster, we've been monitoring this, how these stars move for about 20 years, which is what this is showing here. So each of these dots is a different star that lives in that star cluster at the center of our galaxy. And in particular, we can focus on this one here, which you can see makes a whole complete orbit around something that looks like there's just nothing there, right? And so that was sort of really good evidence that there must be a black hole at the center of our galaxy. It's something that weighs about 4 million times the mass of our sun, but it doesn't give off any light at all, really. And so this is just showing sort of, as we've monitored this, we've been able to constrain the mass of that black hole very well because we've been watching it for so long. So what if we were able to take another step further? What if we were able to keep zooming in to try to see the unseeable? If we were able to do that, we might see something that looks like this. This is another computer simulation. It's a little hard to see on this projector, but what you're looking at here is sort of the chaotic motions of all the material that's in a disk that surrounds the black hole at the center of our own galaxy. And so you'll see a lot of sort of stuff moving around, a lot of bright spots that come and go. If you have really good eyes on this projector, you might be able to see some faint stuff that's coming out of either end as this black hole is ejecting a jet of material. But the one feature that you might actually notice is that this looks like a circle there. And that's actually the shadow that the black hole is casting on the material around it. So for example, if there's light behind this black hole, it's not able to reach us because it's getting sucked into the black hole. And so that's sort of the signature that we're looking for. So why does a black hole cast a shadow? Well, it's a little more complicated than the reason that we cast shadows or trees cast shadows, for example. With black holes, the key is that general relativity tells us that black holes bend space-time. And that bent space-time tells the light how it should move through that bent space-time. And so if we have an example like this where we have a bunch of random light that we're just sort of throwing at the black hole and asking where it shows up, some of those light rays will make these sort of loop-de-loops and sort of get bent around and back towards us. But the combination of all of these different directions of light from this disk of material that surrounds the black hole all sort of add up and combine to make that sort of that shadow of the black hole that we see in this final picture. So if you might ask, like, where should we look if we want to actually take a picture of a black hole? In the end, there's really only two good options. So there's two things we want if we want to make a good image out of a black hole. We want the material around the black hole to be very bright, and so that is high on this plot. And we also want to be able to resolve fine details, as fine as we can. And so that means that we want black holes that are very big and that are close by as we can get them. And so in the end, there's really only two good options. One is Sagittarius A star. This is a black hole at the center of our galaxy. It's quite bright. The material around its disk, because it's so close to us, is very bright for our telescopes. But it's kind of a piddly little black hole as far as things go. It only weighs about 4 million times the mass of our sun. The next best option is this black hole called M87 star. It's the black hole at the center of the M87 galaxy, which was on the very first slide of this talk. And that one weighs about 6.5 billion times the mass of our sun, but it's much farther away. And so the combination of those two things mean that we can get roughly the same amount of detail for these two black holes, even though they're very different. So what actually sets the amount of detail that we can get from a telescope's image? There's really only two things that matter here as well. The wavelength of light that we observe and the diameter of our telescope. So basically, if we have a bigger telescope, we can resolve finer details of an image. For the observing wavelength, we're kind of set by nature. This little video is showing you what the black hole at the center of our galaxy would look like as you move from a wavelength of 1 centimeter down to 1 millimeter. And so you can see at the start of this video, when it plays again, that at 1 centimeter, you're really overwhelmingly dominated by this jet and this huge disk of material. And so you basically cannot see all the way down to the event horizon of the black hole at all. On the other hand, as we get to shorter and shorter wavelengths, we're able to peer down all the way to the black hole's event horizon. And so we're basically confined to observing at 1 millimeter in wavelength. So the question is, well, how big of a telescope do we need in order to resolve the event horizon of this black hole? And so the answer is that if you run the numbers, you find that you need a telescope that is literally the size of the entire Earth. So this is impractical, as it turns out. Nobody really wants to live underneath a giant telescope. And in fact, we don't even have any Bond villains or eccentric billionaires to cover up worthless parts of the Earth like Oklahoma. And so we're stuck with having this vast globe that we have basically no telescopes on whatsoever. And so we have to come up with a much more clever technique in order to make an image of a black hole. And so this is where the Event Horizon Telescope comes in. The Event Horizon Telescope is not really one single telescope. It's not one facility. Instead, it's the conglomeration of literally every single radio telescope on Earth that can do these kinds of observations. Literally every single one has said, yes, this is an important thing that we should do, and joined in with this collaboration. And so we've built up this network of telescopes that span the entire globe, ranging all the way from literally the South Pole all the way up to Greenland. This one is not yet online. It will be later this year. With many different facilities in between. And so you may see from some of these pictures that some of these radio telescopes are themselves composed of individual smaller radio telescopes. And that's kind of the more common way that we observe in the radio wavelengths. And so this is a video that's showing the ALMA telescope in Chile. But the basic idea is that we get all of these telescopes to work together. And so in the case of ALMA, like this, all of these telescopes are actually physically connected. We can actually run fiber optic cable out to every single one. They all go back to the same building. And so this is actually relatively simple compared to more complicated cases. And so as this video goes on, you'll see them all sort of dance around in sync because they're all observing the same thing, and we're combining the light from all of these individual telescopes together in order to fake having a telescope that's as big as however far apart we can set those telescopes. So obviously, again, nobody is going to let you run fiber optic cable from the South Pole all the way to Hawaii. That would be fantastically expensive, but fantastic if we could do it. So instead, we again have to be a little more clever. And so there's a couple of key pieces of technology that let us do this. One is that we need incredibly, incredibly stable clocks. So the way that a normal mirror works is that we bring all of the light from different parts of the mirror to a common focus, and we do that all at the same time. But of course, if we have a telescope in Hawaii and a telescope in the South Pole, there's no guarantee that we can bring that light to the same place at the same time. In fact, we definitely can't, because we can't move things from the South Pole anywhere. It's very difficult. And so what we need instead is this incredibly accurate clock. And so we actually timestamp that light as it comes in to our telescopes at a rate that's accurate to like a part in 100 trillion or something like that. These clocks only lose about 1 second over 100 million years. But nevertheless, when I was observing for the Event Horizon Telescope in Arizona, this clock actually just lived in a closet in a bedroom in the telescope, and it was really noisy, and so it was kind of hard to sleep. So that shows you just sort of like, the power of this technology, but also its common annoyances. And the other key piece of technology is that we've really improved our electronics and the ability for us to gather the light from our telescopes. So all of these like white boxes here that are actually just stickers on top of black boxes, these are all hard drives. And so when the Event Horizon Telescope is recording actual data, every single site has to write to 8 hard drives simultaneously just in order to keep up with the amount of data that's coming in. And so then when we want to combine all of that data, we just take out the hard drives, we ship them all to Boston, and then we run some fancy supercomputer algorithms on that data. And so these are kind of the two main pieces of technology that have made this really possible. Especially having the ability to record tons and tons of data for relatively cheap has made this all a lot easier than it used to be. Okay, so hypothetically, what would we see if we did have a telescope that was the size of the entire Earth? In this case, I'm going to represent what we actually measure just with this blue circle inside this white box. Trust me, it's better that way. You don't want to know the details. But we can take those measurements and we can turn them into an image. And you'll notice in this case that this black hole is still pretty blurry. There's not a lot of fine detail. And that's basically because we're still limited by the size of the Earth. We can only resolve details as fine as however big the Earth lets us do. So this is fine. Now, what about the case where we are not able to cover the entire Earth with a telescope? In this case, we're limited by the geographical locations of each of these stations that compose the EHT and how long we're able to observe this source for as the Earth rotates. So unfortunately, in this case, we have many fewer measurements, and the result of that mathematically is that there is a literal infinite number of possible images that you can create out of data that look like this. Literally an infinite number of possible images. So that obviously is not good. We would like to do a little bit better. And so what we end up having to do is basically say, well, some of these images are more likely than others. So for example, if I turn the image of this data into a picture and it looks like an elephant, that is probably wrong. On the other hand, if I turn that image into something that looks like this black hole, that's much more likely. So static, unlikely, black hole, pretty likely. And so you might ask, well, what makes this, why do you like, oops, sorry, wrong direction. Why do you like this one much better than the other one? And the answer is that we've developed a very large library of possible black holes. So there was a huge computational and theoretical component to the Event Horizon Telescope observations that's sort of summed up in this. So this is each of these. Oh, I'm pushing the wrong button again, I'm sorry. Each of these is a different simulation. So for example, we've slightly changed how fast the black hole is spinning. We've slightly changed how the disk that surrounds the black hole is set up. And so you can see that even in this case where we have literally hundreds of simulations of a black hole, there are some things that are common, right? So basically all of these have that black shadow in the middle, and a lot of them have that bright ring that surrounds that shadow. And so this is a good way to sort of weed through that infinite number of possible images down to the ones that we think are actually, corresponding to reality. So what happens if you don't have enough telescopes? Well, you get something like this. So I actually observed the EHT back in 2013. We only had 4 stations at that time. Now we have 7. And literally we could not tell the difference with the data that we had between 2 blobs and an actual shadow of a black hole. And so there was nothing that we could really do about that. We were sort of fundamentally limited by the telescopes that we had available at that time and what we had observed. I love this paper because I'm literally like the 100th author on this paper or something like that. Like there's so many people involved in this project, and they are all amazing. And so I was very happy to be, some tiny cog in this giant machine of science. So to put this in another way, this video is just going to show what happens to the actual image of this black hole as we add additional telescopes. So we basically are able to take advantage of the fact that the Earth rotates, and so that changes how far apart our antennas look like, as though you were staring down at the Earth from that black hole. And so you can see that as we go over time, we slowly build up that complete image of the black hole. And so this means that every single station matters. Every single telescope that we can add matters. Usually adding more telescopes is expensive. Like, it costs money to build roads to telescopes, and then to build the telescopes themselves, and then to buy a bunch of hard drives, and then to buy a bunch of beer for astronomers. Like, this is all very expensive stuff. And so we are able to also take advantage of the fact that the Earth rotates. And so that does help us in a lot of ways. Okay, so what have we actually learned from looking at this image? Probably almost everybody in this room, if you are coming to a talk about astronomy, you've seen this picture before. But I wanted to talk a little bit about what we actually know now that we did not know before this. So the first thing we know is that this is definitely a black hole. There is nothing else that this can be. The fact that we actually observe that shadow tells us that there must be an event horizon. There must be something that corresponds to a black hole in this image. The second thing we now know is, very precisely, we know that this black hole weighs about 6.5 billion times the mass of our own sun. We know that to about 10% now, whereas before we were lucky to get to about 50%. That is something that we can get pretty straightforwardly just from the diameter of how far apart this ring is. The third thing we know now is that this side of the disk is moving towards us. It's kind of like if you ever listen to a race car at a racetrack. When it comes towards you, the pitch is higher, and when it goes away from you, the pitch is lower. It's a similar sort of thing here, where this material down coming towards us on the bottom half of this is moving towards us, and it looks much brighter than the stuff that's on the upper part that's moving away from this. You can't really tell from this image alone, but from some extensive modeling, we also know that that disk is sort of inclined out of the screen towards us, and it's rotating clockwise. So in case that's something that you care about, we also know that. We also know very well, because this image is really close to an actual physical circle, like a perfect circle, that this black hole is consistent with general relativity. So this isn't enough to sort of rule out that it couldn't be other things. There are other crazy things that it could be. So whenever you have a physicist and you give them too much free time, they're more than happy to come up with a bunch of crazy theories. And so there are other possibilities that also would produce an image like this, but this is actually completely consistent with Einstein's general relativity. Okay, so coming towards the end of things, you may remember from the very beginning of this that it looked like our own black hole at the center of our galaxy was a really good target for doing this. And in fact, that's true. That was the entire reason that this telescope was built, but we haven't seen the image of it yet. And so you might ask why. This black hole is about 1,000 times less massive than the black hole at the center of M87, but it's about 1,000 times closer. And so we should get about comparable image quality between these two black holes. So why haven't we seen this one yet? Well, the data actually already exist. At the same time as they were taking the data to make this image of the M87 black hole, they were also taking the data to image the black hole at the center of our own galaxy. The problem is one of time, actually. So the M87 black hole, because it's so large, it doesn't change very quickly. If you had, for example, a blob of hot material that was in the disk around the M87 black hole, it would take it a couple weeks to a month to go around once. On the other hand, because our black hole is kind of piddly, that only takes like a couple hours. And so that means that the black hole at the center of our galaxy changes really quickly. It doesn't stay the same. It doesn't stay constant. And so the key is that for the Milky Way's black hole, you can't just make an image of it. You have to make an image of it very quickly before it changes enough that you've sort of washed out all of the information that you once had. And so that's taking a bit longer as far as the data processing goes. Everyone is extremely careful on this team, and so they definitely want to make sure that they're confident in the results that they have before they announce a global press conference. So how hypothetically could we do a little better? Well, if the M87 or the black hole at the center of our galaxy changes so quickly, we need to be able to fill out those measurements. We need to be able to create an image of it much more quickly. So at the top, we're seeing basically the current array, our hypothetical measurements that we're showing up here. At the bottom, we've taken the current array and added just a single satellite that lives in low Earth orbit, and we'll just sort of pretend that that satellite can always join this array. And so what you've probably noticed is that this space of all the measurements has been filled out really quickly in comparison to this case. That's because a satellite in low Earth orbit goes around once in about an hour and a half, compared to the Earth, which takes 24 hours. And so this is a way that we can actually make our images much faster. This still doesn't improve the resolution of our images because we're still limited basically by the size of the Earth. And so if you wanted to really make higher resolution images, you would have to put a satellite in orbit that sort of went elliptically around the Earth. And currently there is no talk of doing that. So I just want to wrap up by saying that this was a fantastic international collaboration. There are literally hundreds of people who have worked on this, hundreds of people who've contributed to the instrument development, hundreds of people who've contributed to the observing campaigns and the analysis work. And so this is just an image of all the people who were present at the telescopes during the 2017 observations, ranging all the way from the South Pole to Spain, to Hawaii, Arizona, Chile, Mexico, and then Command Central in Boston. And so this is, I think, a really good way to showcase the fact that these international collaborations of many, many people can produce these stunning results like this image of the black hole that we've seen. So thanks. I'll stop there and take any questions.
Thank you, Justin. Wow, that was really great. So we're going to enter into the Q&A portion. The way this works is please raise your hand and we will do our best to call on you. Submit Twitter questions if you have those. One of us will do our best to remember to repeat the question before answering. So I see a question right here.
What about the McDonald Observatory? Like, why isn't that cited in your research?
Why isn't it what?
Why isn't it cited in your research as a sustainable telescope?
Sure. So it's definitely a substantial the question was what about McDonald Observatory, which is in West Texas, of course. Why isn't that cited in my research? The answer is, of course, it's a great telescope, but we don't have a radio telescope there, at least not yet. So one other possible way that I didn't really mention was that as we look at this, one possible way to get an image faster is if we just dot more of the Earth. Dot more of the Earth with these telescopes, right? So that would be a good way to sort of fill out that space of measurements.
Dot more of the Earth with radio telescopes?
Right, dot more of the Earth with radio telescopes. So right, at McDonald we only have optical telescopes right now. And so they basically cannot see all the way to the black hole at the center of our galaxy. Yeah.
All right. How about in front of the stairs over here?
Yeah, so the question was, there are other radio telescopes like Arecibo in Puerto Rico, for example. So what's the limiting factor preventing those from also joining this array? And the answer is that it comes back to the wavelength. So in order to do this, we need to observe at about 1 millimeter wavelength. And so that imposes two sort of requirements. A, we need a high mountaintop site with dry air because water absorbs that kind of light before it is able to reach the ground. And so we need to go basically to a desert, which Puerto Rico is not. And the other thing is that because we're observing at 1 millimeter, we need our dish surface accuracy to be much better than 1 millimeter. And so if you've ever seen pictures of Arecibo, like it's literally like chicken wire, right? And so that is not accurate enough to be able to reflect light that is 1 millimeter in wavelength.
Okay, let's go up on the balcony over here.
Would it help if they at some point put a telescope on the moon to make it
Yeah, so the question was, would it help someday if we put a telescope on the moon? I have not personally put a lot of thought into this. My guess is that that would be so impractical that we would rather stick to satellites. Because satellites, at least you don't have to worry about all the moon dust and the crap that comes up from landing on the surface of the moon. So there have been some thoughts about putting radio telescopes on the far side of the moon, but that's basically because we want to prevent interference with actual Earth radio and TV stations and that sort of thing. But as far as putting a telescope that observes at 1 millimeter on the surface of the moon, I think that would be almost as crazy as covering all of Oklahoma with a telescope. So.
All right, let's do one more. How about right here?
Yeah, so the question was, what other theories exist for what that could be other than a black hole? Well, so like I say, it's definitely a black hole. The question is, what kind of black hole is it? So it can be one that's described exactly by general relativity, because general relativity is right, but there could be these other options. So one of them is called a Magnastar, which is basically this like incredibly magnetically active, dense, compact remnant of a star with many other stars that have collided with it. There are other options that I'm not super familiar with. But they're all basically like things that you would read on Wikipedia if you like just kept clicking like related articles. So you just like go off into this nether region of even more progressively weird ideas.
Thank you. Let's give one more round of applause for Dr. Justin Spilker.